welcome. Thanks for showing up. I had some tough competition during this slot, I think. So my name is Jeroen Soeters. It's a Dutch name. I'm Dutch, hence the funny name as well as the funny accent. So if at any point during this talk you don't know what I'm talking about, just raise your hand and I'll try to clarify. So I work for a company called ThoughtWorks. We're a global consultancy business. We actually have an office in Denver these days as well, and we are hiring. So if you're interested, hit me up after this talk. Those of you might have seen this on Twitter. Actually, one second. I might have, with this exporting of the presentation, messed up the presenter view here. This one is not switching. Give me 1 second. And then I'll do this one again. Up. Presenter view. This one, and then this one goes too. Sorry about that. Here. I think it also switched to mirroring or whatever. Doesn't matter. I'll do it without the notes. So for those of you who might have seen it on Twitter, there will be a book giveaway during this talk. That's kind of my attempt to get you all off Twitter during this talk. So the books are here. If you see that image in the top right-hand corner of a slide, that means like put away your phone for a second and pay attention. The first one who has the right answer can choose one of those two books. Cool?
Right answer, right question.
Right answer. I'll have the right questions, don't worry. Cool. So yeah, let me introduce you to the domain first. So about a year and a half ago, we were invited by one of the top 3 CPGs. So CPG stands for Consumer Packaged Goods Companies, to take a look at their supply chain planning domain and their supply chain planning software and see if we could somehow disrupt the status quo in that supply chain planning software. So we went there knowing nothing about supply chain planning nor supply chain planning software, so we started learning about the domain, and one of the first things I can remember learning at least is that this company actually ran their supply chain extremely well. As in, they have a KPI called case fill metric, case fill rate, which is the number of cases they ship out to their customers in time. And that metric is on average like 99.8, 99.9, 99.7%, so extremely well. So what's the problem? The problem is that it takes them roughly 5,000 people to operate that supply chain. So that's a bit much. So what we were asked to do is take a look at this supply chain planning software, what's going on there, can we somehow create a new system that you can operate with less people than now, because a lot of what these folks are doing is actually just firefighting. And as a secondary concern, also take a look at reducing inventory at hand, right? So they keep in their warehouses and their distribution centers fairly safe margins of days of inventory in hand to actually be able to ship things out to their customers in time. So what did we find there, right? Well, we found a lot of SAP, for starters. And so these guys are actually using the older SAP APO planning modules. Anyone here in this audience worked with SAP or SAP APO? APO? Awesome. Usually there's always one guy in the audience that has worked with it. So there's a lot of things that APO... Is that the right answer? Sorry? No, unfortunately. There's a lot of things APO doesn't do. And because of that, they end up with a lot of what they call bolt-on systems to fill in the gaps for the things that APO doesn't do. So give an example, the demand forecasting system of APO that they use produces a weekly forecast. They have a bolt-on that sits on top of SAP, reads that forecast literally from the database table, does some numbers on it, and writes back a daily forecast to the system. And there is a bunch of these systems. There's like 10, 15 odd of these systems. And you can imagine having all these bolt-ons makes it extremely expensive for them to upgrade that SAP installation, right? Because every time they have to go to the next version, and these are mandatory upgrades by SAP, they have to move all these bolt-ons along to the next version as well. And I'm not allowed to like say numbers, but you're really looking into the order of category of like purchasing an Airbus A380 to upgrade that system. And you can look on Wikipedia what that actually means. So what we were also asked to do, like, please liberate us from this SAP monolith that we have here.
Right there, go back to that. I have to get a picture of
Oh, sure. Cool. So let's talk a little bit about supply chain planning, right, and how that actually works. So if you think about a supply chain, it's really like a DAG, right? So it's like a graph, and on one end you have the customer-facing distribution centers. On the other side, you have the manufacturing locations, like the plants, and these are connected with a network of all kind of different sites, right? That might be other warehouses, that might be mix-in centers, that might be cross-docks, and all of these nodes in the graph are connected by transportation lanes. Now, if we talk about supply chain planning, there's actually a bunch of different activities that happen in supply chain planning. So it all starts first with demand forecasting. So demand forecasting is on these customer-facing DCs, generate a forecast, right? So on a specific day, for a specific SKU, for a specific warehouse, what I'm expecting to move out of that DC to the customers, right? Then there's distribution requirements planning, and distribution requirements planning sort of takes that forecast as an input and like pushes that down through the graph all the way to the producing locations. So what the output of that is where you want your inventory in the supply chain and when, right? So for this warehouse, this day, this SKU, this is the inventory I want. Then there's transportation planning. So transportation planning is, well, given these ideal distributions that I would like to have, right, how am I going to move that stuff around, given the actual lane capacity, given how I can put stuff in a truck, how many trucks do I have available, et cetera, how we're going to move that stuff. Then there is site-integrated planning. So site-integrated planning is planning the plant. So if you think about process manufacturing, which is what we're tackling first, in process manufacturing you have a plant, and the plant has many production lines. The one we're working on now is like 30 lines, and each of these lines can produce many SKUs. Now the goal of site-integrated planning is come up with a production schedule such to A, make demand, and B, minimize the number of changeovers on those lines, right? Because those changeovers, if you switch from one SKU to another one, that's really expensive, right? If we make some kind of laundry detergent and we want to switch from one scent to the other scent, now we need to switch the bottles, we need to switch the labels, we need to flush the lines, that's creating a lot of waste, so it's a very expensive operation, so we want to minimize those. And then the last one is raw material planning, right? So given this production schedule, how do I most effectively acquire my raw materials to actually produce that? Now there were two problems that we at least saw with this supply chain, of this way of supply chain planning. And the first one is, as we look at this, is the way I just described this is really how they operate. So it's a very sequential planning pipeline. We coined the term locked, stands for local optimization with constraint transfer, and that's really what happens. So each of these silos, they optimize their own world, throw constraints over the wall to the next one, and then that one kicks in, and so on and so forth. And there's very little visibility down the line. So the distribution requirements planning might push some demand down to a plant, while in that plant a machine is down and it can never actually ever produce that. So that's when those 5,000 planners come in, jump on the phone, and start firefighting to fix that. That's the problem we're actually not going to talk about today. What we're doing for that is we're moving them to more like a distributed global optimization algorithms. If you want to read more about that, a lot of stuff we're doing there comes out of a group led by a gentleman called Stephen Boyd, who leads the convex optimization group at Stanford. And the exact algorithm we're working with right now is called ADMM, and this gentleman wrote the paper on ADMM. Again, that's what we're not going to talk about. We're going to talk about the second problem with the supply chain, and this is Most of these systems, actually all of these systems, they just run once a day. So demand forecasting kicks in at like 2 at night. Distribution requirements planning is 6 in the morning. Transportation planning is 11 in the morning, and then there is the site integrated planning, which happens when the guys come and enter the plant in the morning, and a raw material planning happens off the back of that. So you can imagine time to reaction to critical events in that supply chain is very, very high, as they have to wait up to 24 hours for a system to kick in and compensate for something that goes wrong. So that's the problem that we are going to talk about, is how we are moving this organization from a very SAP-oriented, SAP-heavy, batch-oriented systems architecture to a modern, streaming, fast data, microservices platform. A few examples of systems we're actually integrating with and problems we're solving for them is, one is the plant, right? So here we have a plant and we're producing some kind of dish soap here. We're integrating with our systems at the plant so that when a machine goes down at the plant, we actually can immediately respond to that. Our optimization engine kicks off and immediately re-optimizes the world and potentially offloads that demand to another plant that actually can produce that now. Second is they're currently equipping all their trucks with GPS sensors. So that means if I'm expecting a fleet of trucks at 11 in the morning in Fort Lauderdale and 9 a.m. these are still at the Canadian border, they're probably not going to arrive anymore, right? So by integrating with this system, we can actually attach some confidence to a shipment arriving in time. And once that confidence drops below some threshold, we can again act on that. Yeah, they own the fleet. Part is spot market, part they own. So by integrating, we can actually immediately act on if confidence dropped that the shipment is going to arrive in time, right? And then the last one is their sales order system, right? So say we are running that batch of dish soap there, and that batch is going to end in 30 minutes. Now Walmart comes in and places a giant order for specifically that dish soap, right? If we can immediately respond to that, we're probably going to say to those guys, hey, keep that run going for another 8 hours, and we save ourselves 2 changeovers. Cool. So, really core to the streaming platform we're building is this tool called Kafka. Who has worked with Kafka here? Okay, about half of the group. So you don't need to know much about Kafka for this talk. It's a pretty complicated system, as in it has a lot of knobs and dials that you can tune it for a lot of different use cases. All you need to really know for this talk is that it's a PubSub messaging system, and it's implemented as a commit log. That means I can publish messages on that system on what's called a topic, kind of the equivalent of a queue. What happens is that message gets appended to a log, and then there is other systems that consume from that log, and every consumer basically maintains an offset where it is in that log, and it just keeps on polling and say, hey, give me the last messages as of index 100 or whatnot. Right, so that's really all you need to know. Kafka has 4 main APIs. So it's producer, consumer, connect, and streams. And what I'm going to try to do is I'm going to show you where these 4 APIs are used in our specific architecture, and we're going to see a whole bunch of DDD patterns along the way that enable us to not only build that system, but also build it in an incremental fashion. So first, we're going to start with producer and consumer API. So producer and consumer API, like I told, they're picking messages up. So basically what we ended up with is on a high-level architecture is a very event-driven, reactive microservices architecture. And all these microservices, they are picking up messages from Kafka topics. They're doing some logic on that, and they're producing new messages to Kafka topics. Key thing to note here is that all our stateful services are event-sourced. And Eric mentioned event sourcing a bunch of times yesterday in his keynote. But there is another important reason, besides the one Eric mentions, why we're actually using it. So everyone familiar here with event sourcing? Yep, pretty much everyone. right? So I'm not going to talk too much about this, right? So it's instead of like storing state in kind of a structural model like we have here for our warehouse, where we have like a bunch of outgoing shipments, incoming deliveries, some GIS information, you can actually also represent this as a stream of events, right? And the nice thing in like the DDD world is that this actually, these state transitions, like the idea is these are actually meaningful domain concepts, right? That's worth capturing. That's all good and well, but in a event-driven architecture, there is another very good reason why you should consider doing this, definitely if you have a lot of services with a lot of events going on. And the reason is as follows, right? If I would store within a microservice my state in this structural model, right? So for example, I have a Postgres database with like a warehouse and shipments table. Now I create a shipment. That would mean I have some code lying around that actually inserts that shipment into that Postgres table. But at the same time, I also have code that creates like the shipment scheduled message, right? And publishes that to the rest of the world. And that's a very dangerous situation, right? Because what if I make a mistake? Either I store something in that Postgres database that I did put on the event, or vice versa. Now I have two versions of the truth flying around through my system, right? And it becomes very hard in a microservices system to trace which service actually acted on the right service and which data, and which service acted on the wrong data. By storing all your state in this stream of events, and all that's ever published to the outside world is this stream of events, either you're right everywhere or you're wrong everywhere, but there is no in between. So compensating after the fact is a lot more easier. So I took a snapshot of like just a subset of like the bounded context or microservices we have to show you a little bit of the interaction that these services have with each other. Yep.
These events, where are these events being stored?
We have a Cassandra. We use Cassandra as an event store. We don't use Kafka as like long term. So they're going in Cassandra. And
Cassandra.
yeah.
And so do you do facilitate transaction management between posting the message in Kafka?
No, we don't. We have sort of a polling mechanism that just looks like, hey, is there anything I still need to publish, and then publishes it on a Kafka topics. It's sort of eventually consistent. So this is like a subset of our services, so kind of getting a feeling what's going on in this system, right? So in this case, we have the warehousing service, and the warehousing service indicates to the world, hey, a shipment was created, right? Then there's actually a stream transformation, and we're going to talk more about them later on, picking up that shipment created message. And in this case, what the stream transformation is doing, it's looking, hey, this shipment, this is an outgoing shipment from a plant. If it is, it produces a new plant demand message, right? Because in this case, the plant demand has been adjusted, or the demand on that plant. So that message is published to the world. Then our distributed optimizer kicks in. So the distributed optimizer actually does a bunch of things, but one of the things it does, it ultimately generates a new production schedule. So the optimizer produces, hey, there is a new production schedule generated, and then our manufacturing microservice actually picks up that message. And the manufacturing microservice, that's the one for ultimately communicating with the guys in the plant. Hey guys, there's a new production schedule ready for you, and then they can ultimately decide, are we going to execute on that or not, right? So that's kind of a snapshot of what's happening in the system. So that was producer and consumer API. Oh, sorry. The next one is the Connect API. So Connect is this framework that comes with Kafka that allows you to very easily build secure and very scalable data pipelines. So you can connect systems, like data systems typically, to your Kafka cluster. And with connectors, you have either source connectors or you have sink connectors. And these are like S3 connectors, JDBC connector, HDFS connectors, like a whole world of connectors is there. So the source connectors, they will pull new data from the source onto Kafka topics, and the sink connectors you can use to offload data from topics into whatever system you want, right? So typically, people have like an HDFS cluster and offload every event ever produced into that HDFS cluster. So now where we use Kafka Connect in our architecture, so this is a small subset of our architecture. So this white box is our new like kind of streaming microservices platform, right? I show only two services here, the warehousing and the manufacturing service. Now, we use Kafka Connect to actually integrate with SAP. And we do that in combination with another technique, and that technique is called change data capture. And I want to show a little bit to make clear how that actually works. So CDC it has nothing to do with Kafka, or has nothing to do with Kafka Connect. CDC is like a database native technology, right? So Oracle or Microsoft SQL just have it built in. You can like literally just switch it on. For other databases, there is typically or plugins, right? So for Postgres, there's bottled water, for example, and there's a bunch of other tools available. Now, what CDC does is you point it to a bunch of source tables, or maybe all tables, and CDC then populates a table underscore changes table for you, in which it records all the changes on the original table. So the rows that are showing up in that change table contains some metadata about the operation, right? It has the operation code, like was it an insert or a delete or an update. It has a timestamp, a transaction ID, and whatnot. And then there is the actual data associated with that change, right? So what we do is then we use the JDBC connector pointing to that change table, and we're literally pulling all these raw deltas on these SQL tables onto Kafka topics. And then we pull them to this thing called anti-corruption layer. So if you read on the DDD books, like typically when they talk about the anti-corruption layer, they talk about in these services, right? In like the microservice or in a bounded context, you make a call to another bounded context and you translate that internally, right? Or you get an event and you translate that internally. So yes, we do that as well, but we also have the sort of system level anti-corruption layer. And all these raw deltas that we get from SAP, we pull through that anti-corruption layer, which is effectively a series of stream transformations, and we infer meaningful domain events from them. So how does that work, right? So for example, the demand forecast. The demand forecast, and this gentleman might know there's two tables in SAP with beautiful German acronyms, PBAT and PBIM, and one is like the header table for the demand, and the other is the footer table for the demand, and every column has like another beautiful German acronym, and it works as follows, right? So the SAP, the semantics of that SAP system, as I said, is a batch system. Basically, it runs every morning, it wipes out 18 months of data from a table, and it writes back 18 months of new data, basically shifted one day, right? So that's not something we want to like couple ourselves to those semantics, right? So what we actually do is we have two stream transformations. The first one joins this header and this footer table and does a linguistic cleaning, right? So it translates all these German acronyms to our own domain language. But then we're not there yet, right? Because then still we would get 18 months worth of events every morning. So then we have a second stream transformation. Stream transformation really does the semantic cleaning. So that takes those, what comes out of that first stream transformation, it checks, hey, for this warehouse queue date combination, did the value actually change? If not, nothing happens. If something changed, only then it emits a demand forecast adjusted message, which is the message we're actually interested in. And we do a similar thing for the production forecast. Now, what allows us to do this? This allows us to implement this strangler pattern, right? So strangler pattern, funnily enough, was literally discovered in the wild by our chief scientist, Martin Fowler. He was, I think, hiking in Australia, and he saw these fig trees and these strangler vines. They nested sort of in the top branches, slowly grow down until they like root in the soil, and on their way they strangle and kill the host tree along the way. And Martin thought, that's a nice analogy for a software pattern that I see often, and that's really like incrementally replacing a large legacy system, right, versus doing a complete rebuild on the site and then cut over. There's many reasons why this is a good idea. That's out of the scope of this talk. I just want to show you how we actually do this with this architecture, right? So remember this one. Now, while this is running, actually in parallel, we're building out new microservices, right? And we're building in this case, a demand forecasting service, and we're building that optimizer service that we talk about. And what this allows us to do is, once these services are ready to deploy, all we do is we cut the lines with the anti-corruption layer that was emitting the older events, right? And warehousing service and manufacturing service here, they remain untouched, right? They have no clue that something is happening around them, while actually our new services are producing these events. So this is it's a little bit costly in the sense like these stream transformations are not trivial to write. And in a situation like we were in, there's really no other option, right? Because SAP is a closed source system, and you cannot go in there, change it, and start emitting events from there. If you have that opportunity, that's something you need to evaluate, which is an easier route to take there. The nice thing this allowed us also to do is that actually with this production schedule, we didn't cut the line with the anti-corruption layer. Actually, we kept that line there, and we tagged each production schedule with the source of that production schedule. So one production schedule was tagged with SAP, and the other one was tagged as ADMM. And with like the UI that we already had, we just stored both schedules. And with this simple query parameter for give me the schedule for this source or for that source, we could do side-by-side comparison of these systems in like under 5 lines of code. So that was a nice win as well. Cool. So then the last one is Kafka Streams. So Kafka Streams is a streaming engine, kind of similar to a Flink or a Spark streaming. Kafka Streams is relatively new. When we started using it, it was still in beta. They're like out of beta for a year now, and they're hitting version 1 soon. But though the library is fairly new, the ideas in Kafka Streams have been around for quite a long time, because Kafka Streams has been built by the team that was before at LinkedIn and built Samza, which is another streaming engine. And Samza is more similar in the category of the Sparks and the Flinks in the sense that the operational model is you define a stream transformation and then you submit that to some cluster where some heavyweight resource manager actually goes figure out where to run that, right? And Samza, that was the same. So Samza you had to run on Yarn. So what they thought when building Samza initially and rolling it out in LinkedIn is they thought that they were going to end up with a lot of these analytics type of workloads. But what they actually found out is that a lot of the workloads were really like core domain or core business logic in these stream transformations. And you can imagine if you're testing something with 3-4 services locally or in your CI environment, and half of that code you host yourself in an application and deploy with your own delivery infrastructure like Docker or whatnot. And then the other half you have to run on some heavyweight like, resource management cluster. That becomes very tough to operationalize. And that's when why they took a step back with Kafka Streams, and they said, okay, let's actually try to write this as a library. Right? Because if you can use this as a library, now you can just host it in your own code and deploy it the same as your other code, and it becomes much easier to operate. Now, this talk is not so much about how that works in Kafka Streams. If you want to learn more about that, Niha, who is CTO at Confluent, has some really good talks about that. What I want to focus on is 2 use cases for Kafka Streams and some learnings that we had. And the first one is around this CDC that we were talking about. So Kafka Streams, in the basis, it works on this core concept of that there is this duality between streams and tables. So if I have a table, I can take like sort of the changes on that table, right, and convert it into a change log, as in for every key I have a latest data in an event stream. And then I can flatten that again back, right, in a table where I only store the latest version for a specific key. So you can think about this, for example, you have a, say, a click stream, a stream of clickstream events, kind of, where you have a user ID, and you have another database where you have user data, sort of this this table here. Now you could CDC data from that table. You know, for a key, I get latest version every time in a stream. What you can do is you can change that stream of user data into a table in Kafka Streams. So I have now a table, K-table as they call it, with for this key I've got the latest version, and then you can join that click stream on that table and you can emit like an enriched event with the username, right? And the whole core Kafka Streams is built on these 2 two APIs, KStream, KTable, and you can go from a stream to a table and backwards, and both of them support like the common methods that you would expect on a stream processing framework, right? So they have a join, a map, a group by key, a filter, et cetera, et cetera. Now, this is all nice, but remember CDC, right? We're grabbing stuff from a relational database, and we're pulling these changes onto Kafka topics. This duality here, that looks very nice here, doesn't work anymore when you do this with a relational database. And it's pretty painful because when you hear like the Confluent guys talking about this, a lot of times they're talking about CDC even in the same sentence with this stream processing, right? Or actually in the same sense with this duality. And that just is not true. So you already see the book in the top right-hand corner. So I'm saying this model, if applied to relational database, is not lossless. Why is this not lossless? What information do we lose when we do this in a relational database? No, that's not exactly the answer I'm looking for.
When we go to relations, what data we lose? Sorry.
So that gentleman raised his hand first.
No, I was not answering, I was just clarifying the question.
Oh, wait.
You lose intention?
Sorry?
You lose intention?
That's what we're trying to recreate again, so that's a different problem. There was already no intention in the database in the first place. So.
You lose the last date?
No, it's also not the answer.
What I could see that you lose is you lose change over time. Your table representation just shows the latest, not what has occurred over time. If you turn that back into a stream, you only get what's latest.
No, you would get like every insert update, and so you have to see in this case like this maybe not the best. In this case, the stream that we get is inserts, updates, and deletes from our Kafka from our database, right? So it's the rows in the changes table that we were talking about before. So some metadata about an operation and some data about the operation itself. Yeah.
This is like event sourcing in reverse, right?
It's almost it's very similar, yeah. Anyone? Otherwise, I'm going to tell it for the sake of time, and we'll find another way at the end of this talk for the best question or something to give the book away. No, so what you lose is transactionality, right? And even on one table in that SQL database, someone might insert something, might multiple records at once, and that data gets lost. And that's not a lot of times they mention that when they talk about that. And it's actually the most important thing when very trivial scenarios start to miserably break down in this model, right? So say I have an order and I have line items, right? If I would do this model, so I would have two change tables now, one for the order changes and one for the line items table. Now I can get those two streams, and I can also join those two streams on an order number. But if I want to reconstruct the original order placed event, there's nothing that tells me when I have the last line item or not, right? So that's very, very trivial scenario. And it becomes like if you then think of, okay, now I want to capture the domain event whenever a line item got added after the fact to an already placed order. Well, now I need to know when I see an insert on the line items table, hey, was this line item part of a larger order insert, and is it already being picked up by them, and can I ignore it, or do I actually need to translate this? So very tricky problem. What we actually ended up doing is denormalizing our relational edges, so kind of having really database triggers on that end, putting it into a JSON structure, CDC on that JSON structure, so we have the structure there. It's not ideal. I see other people creating metadata topics, so giving metadata about a transaction, like here, this transaction is coming and it has like 3 events in this stream, 1 event in this stream. A lot of people are struggling with that. I expect probably a year or so that there has been a standard to actually fix this. There's like the BZM guys are working on this as well, or building a lot of these connectors. For now, like everyone is kind of figuring out what's the best way to do that. One of the 2 books you can win today, and actually, funnily enough, came out the same year as the Blue Book came out. Who read this book? Ah, good. Quite a few people. Happy to see that. Yeah, so this book also 2003, and I think it's like just as relevant now as it was then, maybe even more relevant. So what we found out actually during building this system is that a lot of the stream transformations we were implementing are actually patterns from this book, and we like realized that a couple of months in the project, let's take this book, and it's like, yeah, this is that, and so that was quite funny. So I'm going to show a few of these patterns and what kind of problems we solved with those patterns in our like supply chain planning domain, right? So first one is the message translator. It's a pretty simple one. So our manufacturing service here, remember that scenario from earlier on, right, where we showed that new production schedule to the guys in the plant. This one picks up from there, and now the guys say, okay, we're going to execute on that production schedule. So they produce a current schedule changed message. But if you think of it, so a current schedule change message looks something as follows, right? It has like a plant at the top level, then it has an array for the production lines, and then for every production line, it has an array of activities that happen on that line. So that might be a make activity, or actually producing something. It might be a changeover activity, like what we talked about earlier. It might be downtime, any of these things. Hidden in this information lies the production forecast. But you need to do some work to extract that, right? Because if I'm producing some SKU and I have a run that starts 10 a.m. in the evening and ends 6 a.m. in the morning, well, then 25% of that run accounts for the first day and 75% for the second day, right? So a production forecast is, again, for this plant, for this SKU, for this date. This is the value that we're predicting that we're actually going to produce. So by doing this in a stream transformation, effectively implementing this message translator is a natural way of solving this problem, right? Because you don't want to have other services subscribe to the current schedule change and have to do this calculation themselves. So, second one is the splitter. And again, book top right corner, so pay attention. In this case, the sales order service produces a sales order created message. And what happens is, like, a sales order created message has a bunch of line items, and the idea is that every line item is placed against a distribution center. So what we need to do is we need to go to the warehousing service and actually create outgoing shipments for every one of those. So what we did is we implemented the splitter pattern, and the splitter pattern just listens to that sales order created message. And for each of those line items, it issues a create shipment message, in this case a message with command semantics, right? So why would we do this? Why would we not have the warehousing service subscribe to the sales order created, iterate over the line items, and call it a day? Sorry, modify the order? No, that's not...
The shipments could be going to different destinations?
They could, but that would still work even if you like iterate on it, because it would just load or source the correct aggregate and like dispatch to the right one.
For us, it's a volume issue. Yeah, we don't want the warehouse management system breaking out the sales order and trying to determine what shipments go where based on. So we split up the sales order, the shipments for the sales order prior to.
Well, technically, it would be the same thing, right? Either like you do the iteration and the stream transformation, or you would do it in the...
Right, we don't have stream transformation.
Yeah. From a domain perspective, that would be correct. It's more like a technical problem here that would actually, like, too many people.
So maybe if you have multiple entities of warehousing and you're polling, you can have duplicate readings in the warehousing.
No, that's not a problem. Duplicates, yeah, this should always be idempotent anyways, all these things. But
there's too many messages going in, so you get if you split them up, there's less per queue. So if one warehouse needs to read all of them and discards like 33%.
No, it's also not really like that, because what would happen in the warehousing service, it just gets that message, and it would for each, and like in this case, like send the command to the correct aggregate. So that would not be one more chance, and then I'm going to...
Do you have a better chance of optimization your shipping creation if you do it over
No. So I'm going to tell it. So it's actually like a problem. So it is because if something goes wrong, right? So if I send 10 of these create shipment, or if I have 10 line items and then the third line item fails, right? Now, as in every messaging system, there's going to be a retry, right? And it's going to, well, it's going to try to create those first 3 again. That is something like you should have handled with item potency anyway. So that's like it's kind of a secondary concern that you should have solved. But you get this head of line blocking, right? So because that one shipment that's failing is preventing everything that coming after it to succeed. So that's the problem. We'll figure out how to give away the books after, I'll promise. So the aggregator, and this is a really interesting one, right, that is discussed at pretty every event-driven project that I've been on. So this is the scenario here. We have the warehousing service, and the warehousing service publishes a shipments at risk message. Now the shipments at risk message contains a shipment ID, and it contains maybe the reason why that shipment is at risk, right, but not a lot more. Now we have another bounded context or service there that's called incident management. And incident management is responsible for when things happen in the supply chain, and either the system or a user needs to intervene. Like the incident management builds up like kind of this model of an incident there, right? And the incident model management system here needs more than just that shipment ID and a reason, right? It probably wants to know, hey, what was the date of that shipment? What was the SKU? What was the quantity? Bunch more information. So how are you going to solve this, right? And then there's a few things that people do, right? One is, well, probably the worst one is you could enrich the shipment at risk message, right? So you could just dump that information on there and be done with it, right? But that's not a very good solution, right? You're kind of bloating that message, you're coupling yourself to consumers. What if there come more consumers with more requirements? You'll be evolving your schema all the way. There might be conflicting requirements, etc., etc. So that's not really a good solution. Other thing that people do is, well, they build in the incident management service kind of a local model, right? Of say they need these 3 data points from that shipment. So whenever a shipment is created, they listen to that message and they build like a local small model from that shipment. So whenever that incident, that shipment at risk happens, they just have the information locally. Yeah, might work. The problem there is that maybe like 0.1% of all shipments are ever at risk. So we're storing this huge load of data there that we're actually not using at all. Other thing you can do is, well, whenever that shipment at risk message comes, we just go back to the warehousing service, right? So we make sure we have an HTTP endpoint there, and we can actually query that data when we need it. Might work, but there's now a timing issue, right? Because you get the message, and by the time you're actually arriving at that service, things might have changed. So you might not get the exact information that's correlated with that message. So also not ideally. So again here, a stream transformation to the rescue. So what we did is we created a stream transformation that literally just joins the shipment at risk message on the shipment created message. So every time a shipment at risk message comes in, it joins it on the shipment created message, and it issues a new message, again a message with command semantics here that says, hey, report an incident, and that has exactly the data the incident management service needs and picks it up. So it's almost maybe process manager we're building here, right? So we still store state, right? But the stream transformation is now doing that, and it's hiding a lot of complexity under the cover, so you still have to be aware of that. But it turned out to be a very natural solution for this problem at hand here. It is stateful, exactly. But again, this is the this k-table abstraction that actually stores the state now. Yeah. And then this is the last one.
What happens if any one of the events or the other event doesn't arrive at all? What happens?
So we have at least once message of the guarantees for the delivery. So you'll never have an event that doesn't arrive. So the last one, we haven't implemented this yet, so it's more like a suggestion. That's a process manager pattern. And in this case, so a scenario here is we want to create a shipment, but we're looking for someone to move this from A to B. So we open a spot market. So we request that at the transportation context. And then what happens is we publish a message, hey guys, a spot market has been opened, and we do a windowed stream transformation, and the window duration is same to the duration of that spot market. So within that window, we listen for bid offer events from the logistics providers, and once the window closes, we wrap up, we pick the best one, and we actually issue or create the shipment. Cool. So few learnings then. I don't know how much time I have. 5 minutes, perfect. So one thing is if you're going to work with Kafka, use Avro. So Avro is like a schema language and a schema registry to the fullest, right? So Avro is like a schema definition language, so JSON-like, but you can compare it best with like thrift or protocol buffers, but has some interesting aspects to it. And then what you can do is with schema registry, so schema registry is this tool that lets you register a specific schema with a specific topic in your Kafka cluster. Right? So what happens then is there's two steps that we implemented. This first one is that actually in deployed code, the producer will check with schema registry, hey, this message I'm going to produce here, is this backwards compatible with the schema that we agreed upon for this topic? If not, it's not going to produce that message. That was kind of the first step. It's not perfect yet because you still have deployed something that doesn't work, but at least you don't break downstream consumers. And then the second iteration we did on this is in our CI instance, we actually had a schema registry instance deployed where we stored the latest agreed upon schema for all our microservices. And then every time a microservice went to the pipeline, we had a convention where you store the Avro schemas that you're intending to publish within that microservice. And then in the pipeline, we actually check, hey, these are the schemas this guy is intending to publish. Are these backwards compatible? If not, we break the build, and you're actually not able to deploy a service that's not backwards compatible. So a very nice tool is there, so please use that. Another one thing we ran into is a regression test for your data pipelines. So we thought we were kind of in a nice situation with our testing. So for all kind of reasons, we had to mirror our SAP data to a SQL Server database. From that SQL Server, we enabled CDC, and then it went to this anti-corruption layer. So testing was really like we had a Vagrant box, like a Windows box. It had SQL Server installed. It had CDC enabled. We would spin up that Vagrant box. We would spin up like a Kafka cluster. We would literally deploy the connectors. We would drop in the anti-corruption layer. And we would, on one hand, do the SQL insert statements. And on the other hand, we would check if we would get the expected messages, right? The demand forecast adjusted message. So we thought, oh, we're in quite a good position with testing. Well, until we went live for the first time, and we had to pull in 6 years of historical data for their entire North America supply chain. So it turns out there was a lot of crap in that data that are like 3 or 4 SQL inserts, of course, didn't cover. So we ran into like a lot of trouble there. So what we ultimately did is we created these kind of long-running tests that they would kick off whenever you make a change either to the connector configuration or to a stream transformation in that anti-corruption layer. It would kick off a separate pipeline, and what that would do, it would actually pull through these 6 years of historical data, just keep on running, and we would just grab the logs for errors, and it would would break if we would find something. Yeah, it's something you want to think about if you do this type of work with legacy systems. And the last one is think carefully when you're using the CDC, right? If you have an opportunity to publish messages from your legacy system, do some spikes and try to figure out what's actually easier to do. Go the CDC stream transformation way, or just publish and change the legacy code base. So conclusion is really like companies are craving for more real-time data, right? It's not the big fish that catch the small fish, it's the fast fish. Enterprise upstreaming is the future of enterprise integration patterns. So that's all I had for you guys. Cool. Now, best question, best top 2 questions can win the books.
Yeah, I was going to say, we are out of time for this.
Oh.
I think, I was at the center. I think we do have 15 minutes break before the keynote. There's, I won't interrupt your abilities to win a book here, but throw the book and whoever catches it.
That might be
I think that's a blue eye on the book.
they're heavy books.
I have a question.
Yeah.
How do you solve the problem of putting events on the past?
Sorry, events in. Oh, so we didn't do that here. No. Nice question. You win 1 book. Yeah. No, we talked about historic, like kind of a whole different discussion, like temporal and multi-temporal timelines. We actually funny because we did something here because they did want to run what-if scenarios, right? So hey, what if this transport lane had double the capacity? How would I be able to meet my demand then? But what we actually did is we just fed the optimizer with different inputs. Right, we mock different inputs to the optimizer, and that one gives us the answer. So in this domain, there wasn't really a need for creating like branching timelines and figuring out.
So how many of the 5,000 people are now?
That's a good question. So none of them are, so the company we're working with, and that's of course something that we checked before with them, right? Because we don't want to be responsible for basically firing a whole bunch of people. So they have cut down, but most of these people, they're just roles, they're not going to be backfilled anymore. So currently it's still like running parallel, so no one is really like obsolete yet, but they are pretty good at for their people, and yeah.
Follow up, is it still 99.8, 99.9%?
Yeah, they're still like making those metrics, yeah. Oh, 2 questions. Yeah.
So what is the longevity of the data that goes into the K tables? I know that joining in streams is a difficult problem to solve because of windowing issues of.
It's pretty long, yeah. So you have to be clever there that it fits in your data. For some things, you have to basically run them till the beginning of time. So you have to be careful. Typically, though, these are the data sets are not that large because typically, like the data sets your microservices internally store, they're maybe like gigabytes or something like that. But they're never going to be like analytics workloads, right, where you have terabytes or what of data. So I think it's fine for those the workloads we have. It's something you have to monitor, of course, like if you're not running out of disk space on your. It's a good question.
Before you decided on CDC and Kafka, did you investigate any other methods of getting events off of a legacy database?
So we did like investigate. We didn't have like a lot of other solutions. I'm thinking because it's so long ago, they had like a way where they dumped XML files somewhere already for another system. Honestly, it's so long ago that I can't even remember how that thing worked. We started trying with that, and we actually had a Flink connecting to those files, but there were many steps in that translation to ultimately get that data, and it just didn't feel right, and this is like the shortest hop you can kind of get to get to that data, so that's why we switched to this one. Yeah.
So how long did this project take, and is SAP already strangled?
No, it's not strangled, so we're doing this in parallel right now. It took quite a long time, but we started with a POC. I don't know if I'm allowed to actually say entire timelines, but we did like a couple of months POC, really like trying out, that really we trashed. We just took the learnings from it, and then we started building a new system, which has taken now maybe about under a year, but with a fairly large team, because it's a lot and a lot of work. And actually, the biggest problem is most technical problems are solved, but a core is really like the optimizer. That is really like an open research problem. Like no one has really done that before, like model the entire optimization problem into a mathematical model, into a convex problem that you can solve for. And that's really, really a tough task. So we had two guys, I would say one gentleman and one lady. They both have PhDs in astrophysics. The guy actually wrote his thesis on the weight of the universe, who's like solving, just to give an idea of complexity of that problem. And what turns out with this convex optimization is actually funny that a lot of really hard constraints turn out to be modeled pretty simple, and a lot of simple constraints turn out to be very hard to model, and these are typical Boolean constraints. And there's a lot of challenges in communicating that to the client, that you're solving a very hard problem, very simple, but that solving the problem of, hey, we cannot make 2 SKUs at the same time at the same line is actually one of the hardest problems to solve here. So, yeah. Yeah, that's it. I'm going to give the second book to the gentleman with the cap. And
let's get Jeroen another